lesson is on graphing sine and cosine. This is lesson 4.4 from your book. So we're going to talk about how to graph this stuff now. So last time we talked about the unit circle. Here it is. Such a beautiful thing. I love it so much. We have all of these split into sixths and fourths. We filled in all our values. Our square root of 1, square root of 2, square root of 3 over 2. Our square root of 1, square root of 2, square root of 3 over 2. All of those values. We filled in our whole circle. We're ready to go. We want to move on and look at how we can graph these on a regular graph. So the values of sine and cosine repeat every 2 pi. So that's an important thing to remember. If we go around these values, all of these xy's are unique until we go around for another period. And so this 2 pi we call our period for sine and cosine. For the values of tangent, these actually are going to repeat every pi. So we look over in quadrant 1, for example, and we have both sine and cosine as being positive. Well, over here in quadrant 3, we have both sine and cosine as being negative. So when we do that division of y over x, we get those equivalent values sooner than if we go all the way to 2 pi. We have them just after pi. So at this point, this is when tangent repeats, because we're taking y over x. Obviously, in quadrant 4, we have one of them is positive, which is our x, and one is negative, which is our y, which is the same as in quadrant 2 up here. So that repeats also after a pi rotation. So the period is defined as the smallest number c for which f is periodic, or to say more simply, when f starts repeating its own values. That's what we call periodic, when we start having repeated values of those same things. So the period of sine, we said, is equal to 2 pi. The period of cosine is equal to 2 pi. The period of tangent is equal to pi. And all of their sister functions are going to play in the same realm. So use the unit circle. We can plot these values on an xy plane. Our x reflects our input, our theta, and our y reflects our output, our f of that theta. So let's look at some specific values on our unit circle. If we looked at 0, pi over 2, pi, 3 pi over 2, and 2 pi as our x values, we're talking about where are we when we are on our axes. So 0 is the positive x-axis, pi over 2, we're at the positive y-axis, and 0 on the x, etc., and so forth. So the cosine values we talked about, cosine, this should just say cosine of theta, sorry about that. Cosine of theta is equal to x. So we just want to look at the x coordinate where we are on our unit circle. So cosine of 0, what is cosine of 0? Well, we are at 1. Let's highlight some of these values so that they are easier to see. So cosine of 0, that's over here, where at 0 we get a x value of 1. When we are at cosine of pi over 2, we have an x value of 0. At pi, we have an x value of negative 1. At 3 pi over 2, we have an x value of 0. And then again at 2 pi, this is when we start to repeat, we have an x value of 1. So if we wanted to graph that, we could put these on a plane. We could start with 0. We're at 1. Let me make a better dot. 0, we're at 1. At pi over 2, we're at 0. At pi, we're at negative 1. Is that? No. Negative 1. 3 pi over 2, we're at 0. And 2 pi, we are at 1. So that's what our graph looks like. It looks like this nice curve. And it's going to repeat for all of those 2 pi afterwards. So we could just keep going like this. Obviously, that's not a perfect graph. You'd have to actually measure and draw better lines than I do, but that's essentially what happens. We expect that to repeat for all of those additional values. But what we can see is at those specific points, pi over 2, we have a 0, 3 pi over 2, we have a 0, 2 pi, we have a value of 1, and 0, we have a value of 1, pi, we have a value of negative 1. So if we looked at the sine on this, we end up with, let's look at our sine values. Our x's are here in yellow. Let's make our sine in green. So our green, we're going to have 0, 1, 0, negative 1. So we can fill that in. We have 0, 1, 0, negative 1, and then it repeats, so we're going to get 0 again. If we were to graph this, our theta, again, this is sine of theta, sorry about that. At 0, we have a value of 0. At pi over 2, we have a value of 1. At pi, we have a value of 0. At 3 pi over 2, we have a value of -1, and at 2 pi, we have a value of 0. So this means sine of 0 equals 0. Sine of pi over 2 equals 1. Sine of pi equals 0. Sine of 3 pi over 2 equals -1. Sine of 2 pi equals 0. That's going to continue, and if you're having trouble remembering some of those values, you can draw this graph and you can fill it in for more values. That'll help you. So just as in the past, if we adjusted certain values in our equation, it would cause transformations of our graphs. We saw that before. If we had y equals ax minus h squared plus k, our a affected our vertical dilation, our h affected whether or not we were moving left or right, our k defined whether or not we were moving up or down. So we can also do this with sinusoids or when we have sine or cosine. So let's represent this as y equals a sine bx plus c plus d, and y equals a cosine of bx plus c plus d. And we're going to fill in what these a, b, c, and d values adjust within our graph. So for example, if we have f of x equals 2 sine x, 2 times the sine of x. That means for each value derived from that sine of x, we double it. So any value, whether or not it's positive or negative, we're going to double that value. We're going to get a larger value, which causes a vertical dilation. This means the amplitude will be increased by a factor of 2 for that example. If we have f of x, that's what affects our a, our amplitude. A affects amplitude. F of x equals sine of 2x means that before we even bother taking that sign, we're taking a sign, instead of taking it of pi, now we're going to take it of 2 pi right off the bat. So we're going to increase that x value, which means we are going to hit all those points on our unit circle at a faster pace. So you plug in pi, you get an output of 2 pi. If you plug in pi over 2, you get an output of what happens at pi instead. So this means that our period, how long it takes to complete one full cycle, our period is going to decrease by a factor of 2. Or you might say that as increase. We're just going to get there faster. Maybe that is better to say increase. We're going to get there faster. Our period is going to be smaller. So instead of having a period of 2 pi, we are going to have a period of pi, whatever way is easiest for you to think about that. So frequency is the number of cycles the function completes in a 1-unit interval. So frequency is actually the inverse, or I'm sorry, not the inverse, the reciprocal of period, which means that period is equal to 1 over frequency. Frequency is equal to 1 over period. Frequency equals 1 over period. That is equal to our absolute value of our b divided by our 2 pi. So whatever is in front of that x divided by 2 pi is going to equal your frequency. So again, we are at this y equals a sine of bx plus c plus d, and y equals a cosine of bx plus c plus d. And if we want to affect something like sine, instead of just taking sine of x, we take sine of x plus pi. That means before we take that sine, we're going to adjust that x value by a value on the unit circle while we're still hitting all those same values at the same rate. So that means we're not speeding up the process or slowing it down at all. We are just getting to that value at a different time. So unless the pace is increased or decreased by that value b, we said that that value b adjusts how fast we are going, how skinny we are. It makes our frequency go faster, which means we have more times that we are crossing that 0 axis within a shorter period. That's what our b does. Our c just says we're going to shift it left or right, which is the same thing we're used to seeing from that y equals ax squared equation. So meaning that the graph is going to have a horizontal shift by pi. It's not even by a factor, it's just by pi. So we're going to shift left or right by pi, and that phase shift is equal to negative c, that c is whatever we added inside of that sine x plus equation, divided by our absolute value of b, and b is anything if we have that in front of x, because that's going to adjust our phase shift, because obviously we're going faster if we have a b. The last thing is f of x equals sine x plus 1, which means that after taking whatever that value was of sine, we said sine of x, we got that value. Before we complete our f of x, we're just going to add 1 to it. So that means our y value is going to increase by 1, no matter what our sine x was, positive or negative. So that causes a vertical shift. Different than a vertical dilation. A vertical shift is we're shifting the whole thing up. A vertical dilation means we're stretching everything out. So a vertical dilation is a stretch, a vertical shift is a move. And that vertical shift happens for this equation by 1. So we would just move everything up by 1. The graph, also that means that the midline of your graph happens at that point. So before our midline happened at 0, right? That was a 0. If we moved everything up by 1, that means our midline, the middle of this curve, is going to happen at that new value, which would be 1 in that case. So this is a simplification of some of those rules. Let's look at a quick demo. This is called Desmos, and it gives us a way to look at graphs. So this is our standard sine of x graph that we see here. We recognize we have a period of 2 pi. We cross the x-axis at 0, pi, 2 pi, etc. If we were to go out and look farther, it would just repeat, repeat, repeat. That's our sine graph. Sine of 0 is 0, so that makes sense. Well, if we want to look at what happens if we say sine of quantity x plus pi over 3, well, we see that we've shifted by pi over 3 to the left, which is exactly what we expect to do when we have a plus pi over 3 in there. Now we've shifted our entire thing to the left. We haven't adjusted our amplitude. We haven't adjusted our period. Our period is still 2 pi. We still repeat after every 2 pi. We've just shifted it left. Now if we want to look at sine of 2x, so sine of quantity of 2x, we notice that we're getting each place faster. When we had a 0 here, we now have a 0 instead of at pi, we have it at pi over 2 if we were to zoom in. So each of these locations we're hitting faster. That's for sine of 2x. Now if we want to look at sine of x plus 1, we look at our entire graph is shifted up by 1. Our midline here is at 1. That's what we were saying. If we looked at 2 sine of x, that adjusts our amplitude. So now our amplitude, instead of being 1, is equal to 2. These are the peaks that we're going to hit. And lastly, if we look at negative sine of x, we expect a flip around that x-axis, which is exactly what we get.